We're talking about finding the continuous time Fourier transform of periodic signals. And in this video, I've got one example where we start with a function in time, or a signal in time, and find its continuous time Fourier transform. And then in the second example, we're going to look at a Fourier transform and see if we can get the function in time, the signal in time. So let's start with the first one. X of t is equal to a summation of these impulses. So the first thing we need to do is ask ourselves, is this signal periodic? Which seems a little bit ridiculous, being that this is an example of periodic signals, but in general you don't know, right? Taking out of context, you might not know. So you have to ask yourself, is this periodic? And the answer to this is yes. And based on your, or depending on your level of comfort in sigma notation and with the impulse, you might not, or it might not be that obvious. So let's plot it. There's an infinite number of k's here from minus infinity to infinity, and let's just look at the k equals 0 term, for example, just to get us started. So the k equals 0 term, we would have delta of t. So delta of t looks like this, right? And scaled by 1. And then how about when k equals 1? Well, when k equals 1, we have delta of t minus 2, so that's this thing. And you can get the idea. We're going to have 1 at 4 when k equals 2, and we're going to also have the minus k's, so we're going to have something like this, and this goes on forever. This is the periodic impulse train. Choo-choo! We looked at this before, and I'm just going to give you the result. Or I guess let's back up. So is this periodic? Yes, its period is 2. And so omega 0 is 2 pi over 2, which means its period is pi, right? And so if the answer to the question is it periodic, is yes, then the next thing you have to do is find the Fourier series coefficients. So we're going to say that x of t has Fourier series coefficients ak, and what are those? Well, we did this in a previous video, and we did it with a period of t. Here the period is 2, and so we find that the Fourier series coefficients are just 1 over t, or 1 over 2 for all k. So you might have to go back to another video on Fourier series to understand why that is, but we need to use the sifting property, and I don't want to go into that in this video. So those are the Fourier series coefficients. Now, what's the transform? The transform x, capital X, is a sum of shifted impulses 2 pi scaled by 2 pi times ak, delta of omega minus k times omega 0, and omega 0 is pi. Okay, so that's the answer. That is the Fourier transform of this thing. Okay, taken with the Fourier series, you calculate the Fourier series as 1/2, you plug the 1/2 in there, and then this is the expression for x. But let's plot it. Right, this will impress your friends, but it's actually not that complicated to plot. Right, so what do we have here? Well, we've got a bunch of impulses. How many? Infinity. Well, okay, let's plot a few of them. So when k equals 0, I have an unshifted impulse, delta of omega. Okay, so I'm going to draw that unshifted impulse. So here's the origin. What's that impulse scaled by? 2 pi times ak. A0 is 1/2. They're all 1/2. So this is scaled by pi. Great. So what about the k equals 1 term? Well, the k equals 1 term, I have a delta function that is shifted by pi. So I'm going to draw that here. Here's pi. And what's its scaling coefficient? Well, 2 pi times 1/2, pi. And we'll continue on like this. You'll see that I'll have one at 2 pi, and at 4 pi, and at minus pi, and at minus 2 pi. And these are all scaled by pi. And so this goes on forever. That's the answer, right? No big deal there. NBD. It looks more complicated in math terms because the impulse is kind of cumbersome to work with. Okay, but once you start plotting it, you see that it's really not that difficult. Moving on to the second example, find the signal g of t with the Fourier transform shown below. So this is going the reverse direction now. We've got the transform and we want to find the signal. So remember, if in the first part, or when we had x of t, we wanted to ask ourselves, is this a periodic signal? So we want to do something similar here. Ask ourselves, is this periodic? Is the signal periodic, though? The Fourier transform does not need to be periodic. So how can we tell if the signal is periodic, right? From the Fourier transform? Well, a periodic signal has a transform in this form, meaning it has a sum of impulses that are regularly spaced by omega 0, right? K times omega 0. So let's look at our Fourier transform, capital G. Is this a transform that has impulses that are regularly spaced? Yes. It has many impulses and they're all separated by 3 units. So we can deduce actually that omega 0 is 3 because that's the spacing. Just like in our problem, omega 0 was pi, and then they were all spaced by pi. So omega 0 is going to be 3 in this case. They are all regularly spaced impulses, so we can conclude that the answer to this question is yes. Yes, we have a periodic signal, so we better have a periodic answer, when we're done with this thing. Okay, so we know then that this thing is in the form, right, of k goes from minus infinity to infinity of 2 pi. I'm going to use bk for the Fourier series coefficients for this thing because I already used ak's in the previous example. 2 pi times bk times a sum of shifted impulses spaced by 3, like this. So you got to kind of get a grasp on that. If you're not used to the impulse and you're not used to sigma notation, you got to kind of work with that a little bit. But trust me, this is the form of this guy. So now, what's interesting here is that let's first consider, to understand this thing, let's consider the k equals 0 case, right? Because this is a sum of many different k values, actually infinity k values. But let's just look at the k equals 0 term. K equals 0 term, then I would have 2 pi times b0 times an unshifted impulse. Well, here's the unshifted impulse right here. That's the unshifted, right? So that corresponds to k equals 0. So what's the coefficient, the scaling coefficient of that unshifted impulse? Pi. So that means that the scaling constant there has to be equal to pi. So what does that make b0? 1/2, right? If b0 is 1/2, then the scaling constant in front of the impulse would be pi. So just from kind of observing the Fourier transform and form-fitting it, I can just deduce the value of the Fourier series coefficient. Neat. All right, let's try the k equals 1 term. Okay, so k equals 1 term, I would have 2 pi times b1 times delta of omega minus 3. So I'd have an impulse shifted to the right by 3. By golly, that is this one here. Did I just say by golly? My mom would be so happy. Anyway, this is the k equals 1 term. The k equals 1 term is shifted by 3. So this k equal 1 term, and so the scaling constant there is pi over 2. So I need this scaling constant to be pi over 2. So what does that mean about b1? What does b1 have to be? Well, it is 1/4. And if we did the same analysis for the k equals -1 term, by golly, you would find, here's the k equals -1 term. It'll be shifted to the left by 3 units, you will find that b minus 1 is equal to 1/4. Same thing. Great. Let's look at the k equals 2 term. K equals 2 term tells us from here that we would have 2 pi times b2 times an impulse shifted by omega minus 6. Okay, well here's a shifted impulse, right? To the left by, or to the right by 6. This is the k equals 2 term. Okay, here's the scaling coefficient, pi over j2. So what does that mean about b2? This has to be pi over j2. So that means b2, it looks like, is 1 over j4. Right? If b2 was 1 over j4, then I'd have 2 pi times 1 over j4, and that would give me pi over j2. Awesome. So we're moving right along here. Let's look at the k equals minus 2 term. K equals minus 2 term. Well, if I plug minus 2, k equals minus 2 in here, then this would be 2 pi b minus 2 times the impulse of omega plus 6. So this is an impulse that's shifted to the left by 6. Well, that's this one. So this is the k equals minus 2 term. Okay, here's the scaling coefficient. So this thing in front of the impulse has to be negative pi over j2, and so that implies that b of minus 2 is equal to minus pi over j2. You see how we're getting this here? We're getting the Fourier series coefficients just by inspection. Forget the math. Just by inspection. Okay, let's plug in k equals 3. Well, I would have 2 pi times b3 times a shifted impulse by 9. Shifted by 9. Uh-oh. I look at my Fourier transform. I spelled transform. Transfrom. That's awesome. And I see that I do not have an impulse there. So what's the scaling constant have to be? 0. And so what does that mean about b3? b3 equals 0. And what does that mean about all the rest of the b's? Yeah, they're all 0. So the ones that I've circled in red, those are the only ones that I really need to pay attention to. So I'm going to erase this, give us some space. Direct your attention to the top here. I'm going to erase this. Alright, so remember we're after the signal, the period, and we deduced that the signal was periodic. Well, we have its Fourier series coefficients. So now this is great. We're going to call our signal g of t, right? Because its Fourier transform was capital. We can synthesize it back from its Fourier series coefficients. Remember, the synthesis equation was we add up all of the harmonics, bk e to the j k omega 0 t. You remember that? Fourier series. Okay, well, what was the fundamental frequency again of this thing? We said omega 0 is equal to 3. So this is jk3t. Great. Okay, so we've got an infinite sum here, but all of the bk's are 0 except for these 4. These these 5. Forgot to circle this one. These 5. So I just need to consider those 5. So I'm gonna do this in a strategic way because you'll see that these things make nice sine waves and cosine waves. But let's consider the k equals 0 term first. So b0 is just 1/2, so I would have 1/2 e to the 0. So that's just 1/2. Now let me consider plus, right, because this is a sum, the k equals 1 term. K equals 1 term would give me b1, which is 1/4. I'm going to write it like this, 1/2 times 1/2. E to the j, k is 1, e to the j 3t. Okay, so that makes the 1/4 e to the j 3t. And then let's consider the -1 harmonic, or the k equals -1 term. That is also 1/4. So I'm going to write that as plus because of sum, 1/2 because I've factored out a half already, e to the minus j, minus because k is -1, 3t. Okay, and why did I write it like that? Yeah, because that's a cosine, right? We'll get there in a second. I'm going to do something similar for the sine for the second harmonic and the minus second harmonic. So if we look at the k equals 2 term, we would have b2. b2 is 1 over j4. I'm going to write it like this: 1/2 times 1 over j2 e to the j6t, right? Because k is equal to 2. And then I've got a minus, so I'm going to write minus. The -2 term, b minus 2, right? b minus 2 is minus pi over j4. This should have been j4. This should have been j4. So you can go back. I'm sorry about that, but that should have been j4. And so we've already factored out a half, so this becomes 1 over j2 e to the minus j6t, like this. And again, why did I write it like that? Because this is now 1/2 cosine of 3t plus 1/2 sine of 6t. Awesome. That's the signal. So that's pretty cool, right? So now you could take this, and now you can turn it into a a regular problem, I guess, if you want to go back from time to frequency. Take this now. This is periodic, so if you find its Fourier series coefficients, put it in this form and see if you can get capital G as the Fourier transform.